Okay, so I'm going to start off just by looking through the course outline. I'm going to chat a little bit about how I like to run the course and stuff, and then we'll get into the first lecture, which is on linear algebra. If you want to follow along on the slides, I did put them up on Moodle last night. If I do forget to ever put them on Moodle before a lecture, please remind me and I'll come to it there on the spot. But I should hopefully remember. So anyway, my name is Devon, if anyone hasn't met me. My office is in upper ground floor, room number 11 of Mathematical Sciences Building, or TW Computer Building. My consultation times, I find that having a set consultation time doesn't work, because then I sit like alone quietly for like 2 hours every week, and then the week before a test or something, then it's not enough time. So what I tend to do is, and I'll chat a little bit more about this now, I run a Discord server, and on Discord is how you and I will communicate. It's also how you guys will communicate with your tutors when you get allocated them. And as a result, we can kind of try and find times to meet. If you want to meet in person, do like a whiteboard session or kind of go through tuts or anything. But more often than not, what people tend to do is they'll do their tutorials on paper and then send them to me or the tutors to mark. And that works pretty well. So I think it's kind of up to you guys how you get in touch with me, whether it's Discord or email. But if you do want to meet me in person, then try, you need to just get in touch with me beforehand. This course, the description stuff you can kind of read in your own time, but it is just a math course. It is, for those of you who are at the honors induction, it is mainly, I think, targeted at having a new perspective of maths that is a little bit, maybe hopefully not as intimidating or not kind of as abstract as potentially had been taught to you. I don't know what your relationships with maths is, but I kind of hope that by the end of the course you like maths slightly more. It's a little less of a vague notion. And the way we go about this is I'm going to try and do things very geometrically. With that said, the first few lectures tend to come out, especially when we start a new concept, they come out with a lot of definitions and a lot of like formal notation and stuff like that. I kind of like mix between, here's the notation, here's a bunch of like jargony stuff, and then we'll move on to some intuition. So sometimes if you feel like it's getting really in the weeds, you might just need to like bear with me through some of the content. But hopefully by the time you get through to like a test or something like that, these ideas, we've kind of gone deep enough into them that the ideas are starting to like set in and stuff. What you'll also maybe think is that the course is going super quickly up front, and then you'll realize that actually it's going super quickly so that we can like repeat as we go. So for example, I teach linear algebra from the perspective of bases. I think bases is the only way to like understand it. That's obviously not a controversial statement, but for example, if you teach it the way I do, then singular value decomposition falls out, but we have an entire lecture on singular value decomposition. And so that just ends up becoming a lot of hopeful review. So we'll see how it goes. If that's not working for you guys, and it just like so happens that maybe you guys are thinking about maths in a different way, please do communicate with me. I can always try and tailor my way of thinking to you. This is my perspective on mathematics. What you'll find, and I bring this up in a couple points throughout the class, what you find about maths is that a lot of the times it's about having the right analogy in your head. It might not be a perfect analogy. It might not always be the kind of completely correct thing, but if you know kind of like in a certain scenario with linear algebra, I can imagine something as being a line on the ground, for example, to make it less abstract, then that's what you deal with. That you have that in your mind going forward while you go through these concepts, and then if that ever fails, then you just switch to a different kind of mental model of what's going on, and you build up these tools, these little analogies for mathematics that make it more tangible to you. And hopefully, as we go along, you'll be introduced to my mental models, the kind of things that I use to simplify things in my head. But they might not work for you. If they don't, again, please speak to me or whatever. We can try and find a shared language for maths, I guess. Anyway, that's my philosophical rambling. As far as practicalities, there's a Discord server. Please do join the Discord server. It will make life significantly easier. On the Discord server is a ticketing system. It's in one of the little channels there, like a button that says open ticket. Please don't write your messages in that channel, because that'll just push the button to the top. I will also just come through and delete it like 2 minutes later. Please click the button that says open a ticket. It'll make a new channel for you with me and the tutors. And you can put whatever you want in there. You can relate to the class. You can put whatever you want in there related to the class, ask us your questions, and do all that sort of stuff. Sometimes, depending on block and what's going on, the turnaround time on the tickets might get like slower or quicker or whatever. I try at least the day before a test have no tickets open or no tickets unanswered. It's up to you guys to close your tickets when you're ready. But that's kind of the deal I try to do, kind of maintain to. But if you open a ticket and it feels like I'm not looking at it, and you can see a whole bunch of other tickets going away, feel free to just like ping us, and then we'll try to respond when we can. Yeah. Otherwise, as I said, my office consultation is on agreement. The ticketing system, you can do that whenever you want on Discord, and then I'll respond when I can. And then lectures are a unfortunate Friday afternoon of mathematics, especially when we have a test or something. It's not ideal, but we move forward and we deal with that. One thing I will mention just about the videos and stuff is, I'm sure by now you're aware, Witz's Wi-Fi is not ideal at all times. There are many cases where the Wi-Fi might just drop, and in that case, the video drops and all that. I try to not move on, unless we're really starting to run low on time. I will kind of stop and wait. It gets a little bit frustrating. Last year it was a bit frustrating. Hopefully in this venue, it's not terrible. The Wi-Fi here is terrible, but I'm now just doing it off my phone. But again, things might just, happen that the recording drops. And if you are joining online, you need to understand that that is just a risk you're taking, right? Like, it's for your convenience that it's online to stream, but at the same time, if something happens in the room that I can't control, I might just move on. Just have that in mind, but I will try and be as accommodating as I can in all of this as I go. The textbook we'll be using is the one by Mark Daisenroth. It's called Mathematics for Machine Learning, first edition. It's free online on GitHub. You'll kind of find that there are cases where I might deviate from it in the slides. Again, particularly when we're talking about things like changes of bases, I have a very specific way that I like to explain and think about maths. So, use the textbook, but at the end of the day, the slides and our discussions and lectures and things like that is kind of mainly the perspectives I will be taking. What I can promise you for this course, your tutorials are reflective of your assessments. Okay? Anyone who's retaken this class or has people who have taken it before know that I test from the tutorials essentially. Obviously, you're not going to see the same question. I'm going to try and make sure that you're understanding maths and not just memorizing your tuts. But at the end of the day, if you do your tutorials and you get them marked and you engage with that aspect of it, you'll be fine. There is a solutions kind of booklet online of it. It has many mistakes in it. Do not follow that, or if you are going to follow it, check it. In the past, I didn't tell people, but then we would have a test and then everyone would get something wrong. And then I ask why, and be like, oh, the book. So there are no formal solutions that I'm aware of online for this Daisenroth textbook. I also do not like giving out tutorial answers, because what happens is then everyone opens them, looks at it and goes, oh, I know that, and then moves on, and then the test goes badly. So at times I will seem like I'm very strict on tutorials, and it's true, I am. I think that you guys doing your tutorials is the one thing that I tend to try and really push, and then in everything else, your lecture attendance, your consultations, however you want to engage with your lecture material, that's up to you. Tutorials is the one maybe non-negotiable of the course, in my opinion. Cool. You guys can go through the content and stuff. As far as grading is concerned, so I am considering doing a kind of changing it up. So in the past, what we'd do is we'd do 2 block tests, so 1 block test per block, and then you'd have 2 exams. But I find that, number one, what happens is that then we just get this massive test that we dump on everybody, and you only get your first feedback from the course roughly 5 weeks in. And I find for a lot of people that was quite stressful. This can be a fairly stressful class initially. And so I think what we're going to try this year, and it's up to you guys to give me your feedback, is I'm going to try to do shorter 1-hour tests the first hour of lectures. So if you guys want to go home on Friday, you can. And we might just do it here. So I need to, that's the one uncertainty for me right now, is I need to go and get the final count of how many of you are enrolled and how many seats are in this room, and whether or not I can feasibly run a test here. If not, it might switch back to block tests, because then I'm going to have to book off a lecture so that we can go sit somewhere else and actually write a test. But ideally, we can just do it quickly for an hour in here. We'll take your papers, go get marked by the tutors, and then you and I can have a lecture for those who kind of want to stick around. But I will confirm that. But that's what I'm thinking now. As you can see, there are 2. There's no one online right now. Yeah, anyway, as you can see, there are 2 exams for this class. What I try and do is I try and make sure that every hour of assessment gives you 10% on the course. there's no difference then in that fact between exams and tests. I find that, again, some people based on past experience, they kind of get in their heads a little bit with exams, or, you know, this fact that they have like a lot of bigger assessments in a row is quite stressful. So I don't really enjoy the idea that exams are somehow weighted higher, or like a minute of exams is weighted higher than a minute of tests. It's literally just the same thing. Every time you sit an exam or sit in a test for MFDS, your 1 minute of your work will count the same, and then we'll just kind of average how well you do across those minutes, and then you get a mark at the end. And that's kind of the thing. The only downside of this is then that we have 2 3-hour exams, each counting 30% of the class. Okay. But most people, as much as it sounds terrible now, most people like that, because it means that your exams are not rushed. It means that your content is not kind of crammed in the day before. What's up, Manny?
So this will happen in both exams and that
correct. No, yeah, exactly, correct. So the first one will be in week 1, hopefully, and then the second one will be in the 3rd week of exams. We try to space them out for our own marking and then just for your own studying. Cool. And then, yeah, your class tests will be spread out throughout the week. There's a tentative schedule that I'm coming to now. Cool. Good. All right, we spoke a little bit about tutorials. So yeah, please just make sure you try to do them if you want to do well in the class. Here's the weekly schedule. So again, things don't always go according to plan. We might have to, yeah, what's up?
What time do you have any questions?
No, so the way the tutorials work is I will just put online the PDF of questions I want you to do. Some of them are from the textbook, some of them are like kind of custom questions, more in line with, again, what I like to teach. And then you just do them, and if you want us to mark them, you can send them on Discord, we'll mark them. If you want to chat to your friends about them on the Discord server, on the general chat or whatever, go nuts. But there's no like dedicated time to tutorials, it's just on your own time when you want to do them. What's up?
Do we DM them to you or like a channel on them? Because I just see on the Discord there's only help right now. So
there should be another category there called tickets, right?
Is that where we?
Yes. No, well, no. So on tickets, there's another channel that says get ticket or open ticket or something. You click that, there's a button on it. And you then press that button, it'll open another channel under the tickets category with just you, me, and the tutors. And that's where you drop your stuff in. Yeah. And then when you're done, there's another button that says close ticket. If that's becoming an issue, we can have a look at it. But yeah, it's usually pretty obvious once you get there. Yeah, so that ticket system usually kind of pops off after test 1 and then doesn't quieten down. So the earlier you can actually start using it, it seems that people tend to find it quite useful once they get used to it. Cool. So anyway, the first few weeks today, we're going to start with linear algebra and we'll finish that next week. But ultimately, the first block and a little bit into the second block is just a big review of linear algebra. And again, I try and prioritize eventually getting up to like matrix decomposition is like a big checkpoint for us. But again, it's because matrix decomposition ends up becoming this kind of very intuitive, hopefully like a very kind of clear concept that summarizes all of linear algebra. In my opinion, if you understand singular value decomposition really well, most of linear algebra at that point is kind of understood. But we'll get there and we'll build it up as we go. And then lastly, block 2 is calculus and optimization. That's just a little bit more normal in terms of like what you've probably experienced in calculus already. Because calculus is already very geometric and visual, I don't really feel the need to like kind of innovate on that front. And then lastly, I like to, again, this is padding mainly just for me. So on the week of the 19th of May, I hope that we have kind of a revision week. And then there's also another week where there's a Friday slot that is in a study break session. If you guys want to do something then, I'm happy to be available that week as well to do reviews or go through tutorials or whatever. But ultimately, that week, especially of the 19th of May, we might have to push things down if we have to add in tests and stuff like that. So this is subject to change, but ideally, I would like to follow this schedule. One of the downsides of having Friday lectures is the fact that we get 2 public holidays kind of clashing as well, which doesn't help. But we have enough time to finish the class as far as I can tell up front. So here's the tentative schedule of tests. Again, every one of these tests will be just an hour. Based on one of the chapters. The only chapter that you won't see then in a test before the exam is continuous optimization. So that's usually a thing that you guys just have to like maybe study quite hard before the exam if you don't want to get kind of tripped up by it. But at least every other topic you should get some feedback before the exam. We good? Cool. All right, and then yeah, academic integrity. Please don't cheat. Cool. All right. Does anyone have any questions about the outline or anything? We good? All right. Let's start linear algebra. Okay. So there are a few kind of fundamental concepts in machine learning, and they're all pretty much built on top of mathematics. I don't think that's a controversial thing to say. But ideally, we want to have a good understanding of like vector calculus, linear algebra, continuous optimization, geometry, all these things. The only thing we don't cover in this class is probability and distributions. That got moved into statistical foundations at some point and is now the Bayesian lectures and that. So you will be skipping chapter 6 of your textbook. And that is, kind of now taught in John's class for everyone's taking that. But ultimately, these are all then just the pillars of machine learning, and that's why we take it. What's this these first few slides that I'm going to gloss over, try and argue is the fact that you can't really innovate or completely understand machine learning without understanding the mathematics behind them. I kind of agree with this. I think that's pretty intuitive. And ultimately, what we want is to kind of take you from being the kinds of people who can go into industry and do data analysis or something like that using sklearn to becoming the kind of people who can go into industry and actually make something new and particularly useful and tailor the tools to whatever problems you envision or want to work with. I think this class is more of a practical class. It's not. I don't want to keep it very academic. It's not a math class and like a math theory kind of perspective. I really hope it is actually going to be particularly useful. And I try at some point to teach things like Einstein notation, and there's like particular NumPy functions that work really, really well with Einstein notation, which is a way of representing kind of geometric concepts or representing at least matrix multiplication very geometrically, very intuitively, and it's kind of a very clean notation. So we do a little bit of that, and then also things like automatic differentiation, stuff like that. We teach that so that you actually know what PyTorch is doing under the hood, what JAX is doing. You kind of understand that it is really just absolutely weaponized chain rule and calculus. Okay, so that's the goals of the class. And so we're going to start off. Is it possible to move this somewhere better? Oh, yeah. Okay, so we're going to start off with linear algebra. As I said, we're going to start from the very basics for anyone who doesn't remember or anyone who doesn't kind of feel that they completely understood these concepts before. So we're going to start off by chatting about vectors and what those are, and then how they build matrices. And then we will get to systems of linear equations and Gaussian elimination and how that gives you an inverse. But again, it's going to try and hopefully all be building towards ideas of bases, ideas of representing space, and kind of how you represent numbers within a space geometrically. Unfortunately, or fortunately, depending on how you feel about notation, this starts off with us being speaking about things like groups and vector spaces and affine mappings and stuff like that. So it is, again, fairly notation-y to start, but it builds up towards the kind of bigger concepts and builds out of all of this notation. Ultimately, what I really think is the kind of highlights is building towards what's on the right there, which is the linear independence and the ideas of building up bases and dimensionality reduction. Okay. So a vector. A vector is a fundamental abstraction within mathematics. It is its most familiar use is as a geometric entity. So you guys all have seen on the bottom left the arrows pointing in space. A vector always starts at 0, so it starts at the origin and then points off somewhere else, and you can do a bunch of operations on them. Okay, but what's really important is that most, or at least a lot, of very interesting entities can be understood or represented as vectors in mathematics. And again, this is the difference between, I think, someone who's really good at data science and someone who's just kind of like doing what they've seen everyone else do, is this ability to start representing abstract problems or kind of unclear problems in terms of vectors. So for example, a polynomial on the right-hand side can also be represented as a vector because you end up with something like a plus bx plus cx squared, right? And so then you can go, well, a, b, c, okay? And that very idea is the foundation of things like functional analysis and representing things as functionals. And ultimately, like if you keep going with data science, you'll get to things like Gaussian processes and stuff. And that is like the idea of Gaussian processes is you kind of flatten out every dimension as its own kind of point in space. All right, we won't get to that in this class, but beyond this, but that's hopefully the intuition we're going to start building up is, can we represent everything in terms of vectors or kind of space? Come on. All right. Okay. So ideally, we want to look at vectors just in terms of being a tuple of n scalar values, and the notation is just x is an element. X is an element of Rn. All right. So that means that we had n numbers in this. So for example, if x is an element of R3, then it's x1, x2, and x3. Right. We have 3 numbers there. Let's try to do that. Cool. Okay, and the first, and kind of again, most like building off of maybe high school mathematics, useful points for this is in something like a simple optimization task. And so let's say you're given the following problem. We're not going to solve it immediately. We're going to just use this as our motivation, intuition. So we say you're in a factory that produces n products, so name them n1 to nn, capital N to small n. You have m different raw materials, okay? And for every raw material, they get used to produce one particular kind of product in the system, right? So you have Bi of each raw material available, and the product Nj requires Aij of material Ri, all right? So it gets very notationally, but what you just need to make sure you're matching is that I index there matches there, and then the J index there matches over there, right? Okay, and so the question you might want to ask at this point is like, well, how many of each product should I produce to maximize my resources? What is the way that I don't have any resources, say, on the floor of my factory? How many products of each should I use? And this is the kind of question that linear algebra eventually kind of leads or helps us to answer. Okay, and so ideally what we want to do is represent it in this particular way. So as an example, okay, so we have x1 is the, let's try to see if it's in the notation here. So x1 is the number of product 1 that we're going to produce, right? And then xn is the quantity of the nth product that we're going to produce. And then b1 down to bm is the number of all the resources we have, and that is then linked by the a variables, right? So if I produce 1 element of my first product, then I will use A11 resources of my available B1 resources. Okay, and so ultimately when we sum this together, we're going to look at how many of this one resource we used when we produced all n of our different products. Okay, and we're now going to do that for every single one of the resources we have available. And essentially you set it up as that kind of like independent problem to start. And that's largely, you know, the point of linear algebra is you start off with treating things as independent, right? You're looking at it in a perspective of I'm producing a product or I have resources on the floor, and then you will start to kind of shift your perspective to being combinations of resources. Okay, so in this case, you might be talking about steel and wood, right? Like that's B1 and B2 is the total number of steel and wood I have in my factory. Okay, and then X1 and X2 is desks and chairs. Now, I want to know if I'm going to produce 1 chair, I'm going to use 2 quantities of wood. How much wood, like how much of that total wood is remaining, or how much should I use? And I want to optimize that across those 4 resources. The problem with kind of trying to represent it in this way is the fact that it's very difficult to now try and optimize when you're talking about independent things, right? But if you start to shift your basis, all right, and that's something we're going to come to, you start to shift your perspective of the A1s into a way that now actually directly speaks to the resources of products, it's much, much easier. Okay, and you're going to manipulate the A's essentially to go from talking about wood and metal to talking about number of chairs and number of desks. All right, and as you can imagine, what that's ultimately going to look like is just getting that to be a 1, that to be a 1, and everything else to be a 0. Okay, is that somewhat intuitive? Should I labor that point a little bit more? No, we're good. Someone say yeah. Okay, so again, right now what we're talking about is what quantity of x1 and x, so again, let's just say this is 2, so x2, right? Just two quantities. So I have B1 of wood and B2 of metal, all right? When I produce x1 of chairs, okay, that's going to use A11 of wood, okay? And when I produce x1 of chairs, that's going to use A21 of metal, okay? And then there's the same combination for number of desks. That's the, number of desks, that's the quantity of wood and the quantity of metal that it uses, right? And so I'm now talking about 4 variables there. I'm talking about A11, A12, A21, A22, and I'm trying to find this way to make them all optimal individually. That's a highly coupled system, all right? And that's the whole point, all right? When you have these off elements here, the A21 and the A12, that's coupled, okay? And so that means that now I'm working in a dynamic system. I'm working in something where there are multiple interactions at play. So what I really want to do is get them into a regime or in some representation where I can just read off the answer, okay? And that's mostly of what linear algebra is. We're talking about solving something, but what's really happening is the solution is in there. It's just hard to see. And so what we're going to do is we're going to try and say, well, I don't really want to be thinking in terms of wood and metal on the floor in my factory. What I really want to be talking about is number of desks and chairs I can produce. Okay, while remaining consistent to the fact that I have a budget. And that's ideally and we'll come to this if it's not super clear, like it's not practical yet. But ideally, that's what you want to do, is you want to get rid of these couplings, whatever that means and how you represent your system. But intuitively, what that ultimately moves from is saying, how many desks and chairs am I using? Or sorry, how much wood and metal am I using in the A's? To talking about number of desks. And here is number of tables, okay? And the same thing will happen on the right-hand side. Your budget will go from talking about your budget of metal and your budget of wood, it'll become your budget of chairs and your budget of tables. And that is ultimately what it becomes, right? And it's beautiful that mathematics will work out in a way that the X will stay the same, right? The answer to your X is always going to be true whether or not I talk about number of desks and chairs made, when I'm speaking about my resources available in terms of wood and metal, and it'll be the same if I'm talking about my resources available in terms of desks and chairs. Is that kind of does that help? Yep. It'll become more and more concrete as we go. But ultimately, that's the first thing I find that isn't super clear about linear algebra, is the fact that when we're solving for X, we're really re-manipulating how we're phrasing the problem in A. All right. So the questions you might want to answer: can we find a tuple of x1 to n to solve this? Are there any unique solutions or multiple? In the case of unique solutions, we know that there's one optimal combination of desks and chairs we might want to produce. But if there's multiple, it means that I can destroy a table to produce 2 more chairs, and that will use the same number of resources. So that's another way I can do this. Maybe I can just specialize becoming a chair factory and forget about tables, right? And again, hopefully, once we re-represent our resources away from being number of quantity of metal and wood that I have to being quantity of desks and chairs in my factory, it's going to be much easier to say, oh, well, actually, they're exchangeable. All right. And then lastly, sometimes there's just going to be no solution. We want to ask, how close can we get to that? Also, sometimes I just have these little notes dotted around for you guys while you study. It's mainly just to highlight what I'm saying in class. Okay. So in principle, we can try and directly answer this. At least the first 2 questions use simple algebra. So using a matrix approach is easier and more scalable, particularly for automation. And that's why we're going to start re-representing this problem away from being a system of linear equations to being in matrix format, right? So matrix format says I'm going to take all of these A variables, okay? And I'm just going to stack them into this cube representation here, right? And there is a set format because we know that we want to do matrix multiplication in a set way, but it's the kind of thing you decide on for consistency. There's no fundamental reason it has to be this way, but we just put them in there in this order so that we're consistent with the system of linear equations we just did. All right. Okay. So for the quantity of resource 1 that I used in producing product 1, that's A1. For the quantity of resource 1 I use in producing product N, it's A1N. So again, the resources are put along the rows, and the quantity of actual products tend to come down the columns. All right. Again, that's just that when we do the matrix multiplication, we end up still retrieving the same system of linear equations. Okay, and then lastly, as you would expect, I'm going to now represent X and B. I'm going to stack those numbers in the exact same way. So that's also intuitive here, right? We just literally did that. Okay. Cool. This up a bit. And I know that by now this is probably getting frustrating for those of you who have done a class in this, but again, you'll see that there is somewhat method to why we start this way. Okay, but unfortunately, we're going to now review matrix multiplication, just to be clear on how this works. So I've now taken this representation of A of X, okay? So again, I have columns and rows of A, and then X is just a column vector. In this class, we only think about vectors as being column vectors. In about 3 weeks, I'll tell you why. And I'll show you a diagram of what a row vector means and why we think they're different. But in general, a vector is column and a covector is row. I'm not going to test you on that jargon, and I don't care if you disregard this immediately, but understand that when I'm speaking, I'm thinking, if I say vector, I'm thinking of a column, all right? So we have a vector X and a matrix A, and then if we do matrix multiplication, all we're going to do is we're going to run along the rows here and multiply each index in that row with its corresponding index in X, right? So A11 gets multiplied by X1, okay? A1N gets multiplied by Xn. Once I've done that multiplication of all those elements along a row, I just add them together, and I get a single scalar value out, right? We're now going to do that using every single row in this matrix, okay? And there is, I think, an intuitive way to look at it where it's like, okay, take that row and then do this multiplication down until you get a single sum, all right? As you'll see, that is in itself called the dot product. But I also think, especially when we're dealing with kind of bases and things like that, it's also helpful to understand that what matrix multiplication is also doing is saying, well, I'm going to represent these columns as their own entity, right? So now I have a row vector or a covector of other vectors, right? So what I'm going to say is I'm just going to take this and I'm going to call it A1 bar, all right? And I'm going to do that for all of my columns now. A1 bar, A2 bar, A3 bar, okay? And that is now just a vector. It's just a row vector. And I'm going to do the same pattern of this dot product with X1. And what you do when you get out when you do this is you get A1 times by X1, A2 times by X2. Excuse the handwriting. Okay? And that, to me, is a useful perspective, because what you start to realize is that when you're doing matrix multiplication, what this is a weighting on how much I care about that column in the matrix, right? And then ultimately, I'm going to now just do a linear combination as in a combination, I add them together, linear. All I'm doing is scaling them by x, well, xi, all right? Makes a linear combination of these columns. Okay, and those are two different perspectives of what a matrix is doing. In one version, this matrix is telling me how far x1 moves in a particular direction, all right? That's what that value is there. In the other perspective, what I'm doing is I'm taking columns out of a matrix A and I'm combining them in some set ratio, not so much a ratio because it's not normalized, but some set format or some set ratio of the x1s to xn. Okay? And that now gives me my final vector at the end here. They are mathematically equivalent, conceptually very different and helpful, I think. All right. Everybody happy up to now? We good still? No one lost so far. Cool. All right, so matrices and these kind of quantities in their own right get studied a lot. They get kind of some attention in their own right, and it's important to understand that there are a number of operations we can do on them, and they do on occasion get kind of become very, very useful, especially when you're manipulating entities, right? So, for example, you can add matrices. So if I have two matrices, A and B, and I add them together, then what that corresponds to is an element-wise combination of those two matrices. What is important is they need to match their dimensions. You can't add two matrices that don't have matching sizes. So for example, they must both be M by N matrices. Okay, so a little review on that. The first index over here is the number of rows. This is the number of columns. Okay. Remember when we're speaking, we're saying the number of rows earlier is the number of resources I have, so metal or wood, and the number of columns was the number of products I was producing, right? So it obviously matters when we're doing these problems that we understand how many of each it is and we don't flip those indices around, right? I could be producing 4 products all from metal and wood, and so now I need to have a 2 by 4 matrix to represent this problem, all right? And again, it's relatively deep, and we will get to the meaning of why that, like the fact that you have more columns than rows there, so to immediately be ringing some bells for you guys and thinking, well, how does that work? How do we optimize something like that? All right, but for the moment, all that matters is we can add them. So let's say we have 2 different kind of versions of that problem, and I want to optimize both of them. I can add those 2 matrices together, get one matrix, and then just optimize on that. You know, maybe I have a warehouse in Johannesburg and another in, I don't know, Pretoria. All right. You can add matrices together and you get out to a matrix that is also M by N. You can do matrix multiplication, and what this corresponds to is essentially doing this whole thing over here that I just showed you now, but with multiple columns of x's. Okay, so in that case, what we will represent it as is A times capital X. And now what you're doing is every row of A will get multiplied with every column of X, and you'll slowly start to fill out all these little values, all these scalars based on those rows and columns being paired off. Okay. Important to note is that you can only do matrix multiplication under specific settings when the right dimension of A, so the number of columns of A, matches the number of rows of B, then you can do matrix multiplication. Otherwise, it's not going to happen. Reason being is because you need to be able to pair off A11 must go to X1, A1N must go to Xn. If those internal dimensions don't match, it means you have A1M and then no X sitting there to multiply it with. Or vice versa. You have an XM and nothing over here to multiply it with. So it's kind of just almost nonsensical. And if you've done that, your problem is ill-posed. Something's not going right in the maths. Okay, so those internal dimensions must always match on you. And when they do, what you end up with is a new matrix, call it C, that is now the dimension of the number of rows of A and the number of columns of B. And that makes sense because the number of columns of A just got paired off with the number of rows of B and they become a scalar. So once they get summed together, summation loses those kind of spatial ordering of those numbers. Okay? So you've just added them together, you've got one summary scalar representing what's going on there. And so all that matters to your problem now is how many rows you had in A and the number of columns you had in B. That'll give you a new matrix in this kind of very abstract way. Okay, so why would B and A not be defined? Again, the slides are trying to challenge you on this, but it's just because those dimensions won't fit, right? You're trying to multiply a scalar by nothing. One important thing to note is matrix multiplication is not commutative. So commutativity, and again, this is when we get to groups, we'll review this. Commutativity is when an operation is defined for AB, it means that it's also defined for BA. Now that's obviously not going to be true because in this case, A and B is fine. The internal dimensions match. But if I try to do B times A, what I'd end up with is a K by N, and then a, sorry, now speed that up, K by M, and then on this side would be an N by K. All right, and then those two internal dimensions don't match. So matrix multiplication is not commutative. Important to remember because it can trip you up, especially when you start trying to represent problems in terms of like row echelon form, which you will get to. If you don't do row echelon form in the right order, what you're essentially doing is trying to commute that matrix multiplication, and it can lead to some issues if you don't keep it in mind. There is another version of matrix multiplication where you do just do element-wise multiplication. Some of you may have seen it, some of you may have kind of used it. It's called a Hadamard product. It comes up sometimes in machine learning. It's good to know about, but ultimately it's not something that we're going to be really looking at or using, but it is the intuitive idea of like, I take every element of A, multiply it with its corresponding element in B, and I get a matrix of the same size out. It means a lot, it's a lot less geometrically meaningful. Okay, then identity and transpose, and after this we'll take a quick break. So if I have a matrix A and it has dimensions n by n, so it has the same number of rows as it has columns, it is firstly known as a square matrix. Square because if you actually looked at the matrix itself, you know, same number of rows and columns means that spatially it looks the same in both directions. This matters a lot. It has to be square if you're going to invert a matrix. And a matrix inversion, by definition, is any other matrix of the same dimension, so it has to also be a square n by n matrix, such that when I multiply it on the right or the left of A, it gives me the identity matrix. Okay, that identity matrix will also be n-dimensional. And an identity matrix is a matrix that has ones on its diagonals and 0 everywhere else. It is the matrix equivalent of 1. All right, if I multiply anything by an identity matrix, it doesn't change it doesn't change anything. It keeps the matrix the same. All right. So this, ideally, if you're trying to map this onto real numbers, if I have some real number that's call it A, then the inverse of A is obviously 1 over A is equal to B. And then when I go A times B, I get 1, right? Because ultimately what I'm doing is going 1A times 1 over A, which is equal to 1. Same idea, exact same thing here. And again, in terms of what I was saying earlier, where we're trying to start speaking in terms of quantity or, you know, resources of wood and resources of chairs and resources of desks, rather than resources of wood and steel earlier, what I was saying is I really just want to get an identity matrix on the left. Okay, I was already saying that I want to take something that is a complicated matrix, A1 through A2 and A21 and A22 and all those things, and I just want to try and find a representation of it that gives me an identity matrix, because when I get the identity matrix, I can just read things off. Okay, so you can really see that inversion is going to probably play some role in that. It's going to be an important thing. Okay, so as we alluded to in the first system example, not every matrix has an inverse. All right, does anyone kind of know, given what I just said, does anyone know why we alluded to it in the first example? Because it wasn't super clear. We didn't say it directly. I can go back there and you can tell me which sentence on this slide is the same as saying that it's not invertible. Oh, there we go. Who did say that? Oh, that's done. There we go. Saying that this system has no solution is the same as saying that it's uninvertible, at least in some respect. There is a way to approximate that. Okay, so there we go. These concepts are going to start coming out geometrically and hopefully help us solve problems. Okay, so if an inverse exists, we say that A is regular, invertible, or non-singular. Okay, non-singular in reference to a singular value decomposition, again, which is in 6 weeks, hopefully what we'll understand. And then if an inverse does not exist, we call it a singular or non-invertible. All right, and essentially, if I want to give you some intuition, I promise you geometric intuition for what's going on. What is ultimately happening when a matrix multiplication is non-invertible, right? What a matrix multiplication is doing is it's saying, let's say I have a box here, stacked with balls or like, you know, whatever, air molecules in the box. And I'm going to take this shape and I'm going to manipulate it into another space, right? Maybe I'm going to just put it on its side and now it's a diamond box instead of the box being kind of upright and square, cube. That is an invertible mapping, because what I can do is I can take the box and I can move it over here and I can flip on its side, but I can also put it back, okay? And that moving it is represented by a matrix multiplication A, spatially. If it's not invertible, what I've done is I've squashed the box. Okay? Box is now squashed. I can't now squeeze it back out. I can't tell you of that dimension, that height of the box that I just squeezed, all right? All the air got pushed down into a single dimension there. I can't now tell you whether that air molecule was initially at this height or that height. Okay? That's what makes it uninvertible. There is a loss of information when I do that compression. It's because I've lost a dimension. My box went from a box to a square. And now I can't tell you what's going on for wherever that point I was on with my square. I can't tell you how high it originally was in the box. Okay? The arguments slightly break down if you push them too hard. So I will move on from that example. But I do like the box example because I think it demonstrates an important point, which is the fact that all we're saying when a matrix multiplication is non-invertible is it just means it loses information when I multiply a system by it. That is the whole point of these matrix multiplications. Okay. And then lastly, transpose, I think, is everyone's favorite because it's just a re-representation of a matrix. All we do is we take its rows of the matrix and make it the columns. Okay? So if it was in element A1, 2, it now becomes element A2, 1. That's the mathematical definition. It's defined with this capital T at the top. And if a matrix is symmetric, it means that its transpose and itself are equal. Okay, so a symmetric matrix would be 1, 2, 2, 1. If I transpose this, it's going to get me back to 1, 2, 2, 1. Okay, not sure that needs to be drawn, but there we go. Cool, and that's the transpose. This matters quite a lot. Symmetric matrices have some wonderful properties, in particular in how they play with inversion. And so we are often going to care to talk about symmetric matrices. Particularly, for example, the best example of a symmetric matrix that you guys are going to come to a lot in your lives is a covariance matrix. Covariance matrices are symmetric because what that is doing is saying what is the correlation between a variable A and B. But the correlation between A and B is the same as the correlation between B and A. You can flip those two concepts in a correlation at least. And so you get a symmetric matrix. What that means is now you can transpose it and it still look the same. But that's also really, really helpful because it means that you can actually decompose correlations into being independent systems. One example would be that earlier system of linear equations that I was talking about. If you have something like a symmetric matrix there, you can do a single value decomposition and separate your problem into an identity. You can invert the problem. All right. Here is a list of identities with the inverse and the transpose. The one that catches people up is that one. Don't do that. You can't add two matrices and invert them. Is not the same as inverting them separately and then adding. But there is one or two kind of useful ones, which is to say that A, B inverted. So if you do a matrix multiplication first and then invert, it's the same as inverting them separately and then multiplying them, but you have to change the order. All right. So if it was AB inside the inversion, it has to become BA outside the inversion. The same is true of transpose. Okay. If I go AB transposed, it's the same as saying B transpose times by A transpose. The ordering must be reversed, right? That makes sense because what I was just telling you now is those internal dimensions have to match, right? So if I've transposed them, the internal dimensions became the outside. So I have to reorder that. But this kind of identity is used a lot in some of the proofs that we'll come to later on. Just note that in this case, you can also sum and transpose or do transpose and then sum, unlike inverting. So that's the one difference. I would recommend you remember that one, just to kind of give a hint for future work. Okay, and then we can take a break there, and then we'll come back. Let's come back at 20 past 3. Alrighty, should we let's get back at it? Cool. So last thing just to note is that there is a third kind of concept with matrix multiplication, and that is the fact that you can multiply a matrix by a scalar, and that is a completely different thing to doing actual matrix multiplication with a vector or another matrix. In this case, a lot of the rules, kind of problems with matrix multiplication, don't exist. So for example, matrix multiplication with a scalar is commutative. All right. So if I'm multiplying a matrix A by lambda, I can put lambda on the left or the right. It doesn't make a difference because in both cases, what I'm going to do is I'm just going to take every element of that matrix A by lambda, its element-wise multiplication by lambda. Okay. There are also some kind of neat properties to this, which is the fact that I can first multiply lambda and phi. So if lambda and phi are two scalars, elements of R, I can multiply them together first, then multiply by C, right, where C is my matrix. Or I can multiply C by lambda, C by phi, and then after that get an output matrix and then multiply that output by lambda. Okay, this property at the top here is known as associativity. So associativity in general is when some operator can be grouped in terms of the two things on the left first or the two things on the right first. Okay. Associativity and then commutativity is when the elements can be swapped. So for example, lambda C is the same as C lambda. So scalar multiplication is also now commutative. Right? Bit of jargon, but again, for next week when we do groups, it comes up. Okay. Transposing of these things, there is no such thing as transposing a scalar, or the transpose of a scalar is just a scalar if you want to think of it completely generally. And so if you first multiply by a scalar and then transpose the matrix, it's the same as just transposing the matrix and then multiplying by a scalar after, or whatever you want to do. Okay, then these last two are versions of a distribution property. So for example, if I'm going to add two scalars together and then multiply by a matrix C, I can first multiply the matrix by each scalar and then do the addition afterwards. Right? So it's a kind of like foiling operator that you would have seen before in school. That's called distributive property. And the same thing holds with scalar multiplication and matrices. You can do B plus C first, or you can multiply B by lambda, C by lambda, and then add the outputs together. Okay? These are just a bunch of cool properties, but that is generally scalar multiplication of matrices. All right. Now getting back to the original motivation of today's lesson was this idea of kind of optimizing systems of linear equation once we represent them in terms of matrices and vectors, right? And so the first thing to note is there's two kind of concepts in this. One is the particular solution, one is the general solution. And the particular solution is any values for x1 through to x4 in this case that satisfy this set of equations, all right? But it's specific. It gives a set value to x1, but it might not be the only one, or whatever. So you want to now have a general solution. You want to understand what space of possible solutions of x's would work. You know what I mean? So is there a case where I have a number of options of whether or not they're a number of options to set the x's, or do I just have one x that's that value that satisfies the equations? Okay, does anyone have any, to maybe play the game at the bottom there? Do any of you have any intuition for whether or not this system of equations here has a unique solution? I'm hearing muttering, but I can't actually hear an answer. No. Why not?
The number of equations are not equal to the number of variables.
Cool. So do you think there is a solution to this? Multiple solutions, correct. There we go. Cool. So there are going to be multiple solutions to this problem, all right? But what we want to do is ultimately find a mechanistic approach to solving systems of linear equations and try to understand ideally what is going on in these cases. And again, I think that in this case, it works best to try and think in terms of matrices as a row vector of other vectors. All right. So again, I like saying that this matrix here, I'm going to name the columns C1, C2, C3, and C4. Okay. And then represent that as just its own vector. And if I do that, what I'm doing now is this kind of dot product operation where I'm going x1 multiplied by c1. That gives me a new vector. Then I'm going x2 multiplied by c2 gives me a new vector. All right. And at the end of it, I add all of those up and hopefully they give me my solution. All right. They give me the values that I wanted to set there. Just my perspective of this. But again, it helps you if you're trying to think about whether or not there are unique solutions and so on, because in this case now you can see that there are actually 4 columns to it, as you said, but we only have 2 resources. All right. So we have 4 quote like entities or 4 products that we're producing, and each of them now must kind of add up to use all of our resources. So for example, instead of being in a case where I am a desk and chair manufacturer with wood and steel, I am now have wood and steel, but I'm a desk, chair, park bench, and running out of creativity, podium manufacturer. Okay. Now, obviously, if there's only 2 resources, but 4 different possible products that I can produce from these resources, there's going to be a trade-off of those resources, right? There's no way that I'm not going to be able to at least kind of optimize this by destroying a podium to create a desk. All right. And so ultimately now, as we just pointed out, there are 4 unknowns, but only 2 equations tells us we will generally have infinitely many solutions. Okay. And in this case, the problem has been set up really nicely with a 1, 1, 0, 0 there. Okay. So what this ultimately means is that if I am in a case where producing product 1 just uses 1 entity of wood, so I'm a wood seller, I have it in my factory, and I just sell wood as well. I also sell steel in its own right, but I can also use 8 wood, 2 steel to make a desk, and 4 wood, 12 steel to make a chair. You know, now in that case, obviously I can always then be destroying desks and chairs to try and make, just sell the raw components, you know, wood and steel separately, or I can instead sell less individual pieces of wood and steel, so sell less X1 and X2, and increase my production of X3 and X4 to actually now manufacture the desk and the chair. That's essentially the whole idea here. It's like, what are those ratios that we're doing? And if you have more columns than you have rows, then there's always that trade-off. There's always this kind of, you know, especially if it's 1, 0, 0, 1 in the first 2 columns, there's always just going to be a case where I can use my first 2 columns to produce product 3 and 4, my 3rd and 4th column. Okay. And literally that's what we're going to do. We are actually going to literally try and use column 1 and column 2 to produce column 3 and column 4. Okay. And so if you want to keep this, you know, it kind of comes out in the language of it to a degree, even like if you want to keep this idea that you can use wood and iron to produce desks, or wood and steel to produce desks and chairs, I can use column 1 and column 2 to produce column 3 and column 4. That's the whole thing, right? And mathematically, that is exactly what it means. Let's start getting into that. So firstly, what we're going to do is we're going to take this representation of the matrix, okay, and we're going to FOIL that out. We're going to actually do this matrix multiplication, and we're going to get this kind of sum over here on the right. Okay. We can get at least one possible solution by considering the underlying problem. So we just multiplied it all out. And then if we only use x1 and x2, we can get what's called the particular solution by setting them just to 42 and 8. All right. And all we did here, there was no clever maths. All we did was just read off a solution, right? Because I just want to, for now, satisfy this constraint of 42 and 8 on the right-hand side. And I can see that that's a 1 and a 0. So there's no, like, again, we spoke about coupling earlier. There's no coupling here of wood and steel. I'm just talking with this vector on the left. I'm just talking about wood. And so what I'm going to do is I'm just going to say, you know what? Instead of manufacturing anything, why even bother? I'm just going to sell as much wood as I have sitting on my factory floor, and I'm just going to sell it myself. So I'm going to set X1 to be 42. No other questions involved. Second version of this. Well, I have my steel concept. I have my steel column. So why don't I just also sell all the steel? And I'm going to set now X2 to be 8. 8. And there we go. I've solved my problem. I have nothing left on my factory floor. I'm going to get rid of all my resources, and there's nothing left for me to do. Okay? That is one way that I can use all my resources and sell everything. It's a particular solution. Okay? And that is ultimately what we're going to write down. Entire problem solved. But now what we also want to do is understand the alternatives that I can make. And this is where it gets a little bit more tricky. Also, we're going to, you're not always going to have a nice problem where it's 1 and 0, so you can read it off initially. But what we're ultimately going to say is that if we only use X1 and X2, we can get a particular solution by then setting them to 42 and 8 respectively. And we just, again, know X3 and X4. So we don't produce anything. But is that the only possible particular solution? And the answer is no. This is another one. The fact that there is a negative in it kind of breaks down the whole manufacturing analogy. But ideally, if there's negative, I can go buy more wood. I can go buy more steel and then produce 5.5 desks. And that will also leave me with no resources on my floor, right? There are ways that we can stretch our analogies fairly far. And so we could use either of these to derive a general solution, but by the mere fact that both of them satisfy my initial constraint, which is that I just wanted to use all my resources on the right-hand side. All right. And so in order to obtain a general solution, what we need to do is engineer zeros using the previously unused columns. Okay? And by engineering zeros, what we're going to be doing essentially is moving around what's called the null space. Okay, null space, as in is the space of vectors or solutions that give me a 0. All right, this null space becomes important later on. And so all we're going to try and do is, again, do that whole game we were doing earlier, which is to say, how can I produce desks and chairs from my earlier concepts? How can I produce desks and chairs from the columns that represented steel and wood individually? And so in this case, we're now going to just take column 3, all right, 8 and 2, and try and produce it from my 2 other concepts. And intuitively, it is exactly what I've just said. All we know here is that my chair column uses 8 wood and 2 steel, and I know that those are my chair and steel columns, so I'm just going to say, well, what was the alternatives I could do there? Okay, linearly, how could I change how much I sell of my wood and steel and kind of increase production of a chair? And so that's fairly obvious, from that is the approach. You just literally use 8 of product 1 and 2 of product 2, my raw materials that I also sell, to produce a third raw material, which is my chair. And as you can see, if I take this over to the right-hand side, I have 0. It sits in the null space, right? At the end of the day, all of my resources have been used still, regardless of what I just did here. And so this now corresponds to the vector 8, 2, minus 1, 0. Note the minus 1 in there, okay? Again, it's going to become really helpful in a second. All that happened is we said 8 and 2 in the first column. So I am using 8 of my first resource or my first product and 2 of my second product to produce my third one. But then at that case, I now need to keep it balanced by putting a 0 in there, right? I take this over to the right-hand side, and I get that minus 1. That will always then be the minus 1, by definition of what we just did, because we're always going to be setting up that problem there. Okay. All right, so then furthermore, for any lambda 1 scalar applied to the vector, we will have a 0. So you can always then just go, scalar, and then let's put on the right-hand side, scalar. You still just end up with 0 times by lambda stays 0. It's all within the null space. That lambda is how people lose marks in this class, because they don't put it there, and then it's not a general solution. Remember the lambdas. Remember that it's a lambda in the real space. It is a real number. Anything that you can do there. Okay, we're going to do the same thing for our fourth product. Okay, so this fourth product uses a bizarre quantity of -4 wood and 12 steel to produce this fictitious desk. And so we're now going to say, well, this is easy. I'm just going to use -4 of my first product, 12 of my second product to produce my fourth one, which is, again, very special chair, very special desk. Okay, same story. You can take it over to the right-hand side now, and you get -1, and then it will give you a 0 on the left. And as a result, any lambda times that system, wrong space, any lambda times that system will also be a 0, all right? It's always going to be in your null space. Okay, and what we're going to do is we're going to put it together, all right? So I'm going to say, I want to start off with my particular solution, and there's an error in the slides there, I need to fix it at some point, but it actually gives you 42 up top. So I want to make sure that I'm always using my resources, right? So we know from the initial particular solution that I could have just read it off and said, well, 42 of x1 gives me 42, and 8 of x2 gives me 8 there. So that's done. Particular solution sorted. But now I want to represent how I could possibly move around the null space without changing it. What are my alternative strategies? What's up, mate?
On equation 17, how did that form became negative? This on top plus positive.
Might just be an error in the slides, let's see. Yeah, good point. That should have just been 4 and 12. I'll fix that. Anything else? We're good. All right, thank you for catching that. Cool. So we put it together, and this is now our general solution, which says that either I could just sell all my raw materials, or I could move into the desk and chair production business and produce lambda 1 and lambda 2 of those quantities. And in those cases, I will always still be able to use all of my resources exactly. Okay, and that is my system of linear equations solved. And so that is the entire high-level process. What we just did now is the entire high-level process you're going to do every single time. Okay, you're going to find a particular solution that satisfies my constraints. Okay, you're then going to try and figure out how you can engineer zeros, which will give you your null space. Okay, again, null space is what combination of x's, when I multiply it with a, give me 0, right? And so now you will combine those two solutions, and that creates your general solution. You can repeat this process up top here with the earlier particular solution if you desire. But there is tutorials on this. Cool. So at this point, it's worth introducing an even more convenient representation for a system of linear equations, which is known as your augmented matrix. But ultimately, it's doing the exact same thing, right? So what this is going to allow us to do is just manipulate both sides really easily. Manipulate both sides of the equation really easily. Okay, so for example, if we have this system of linear equations here, where now it isn't as easy as it was where we had that kind of 1, 0, 0, 1 solution earlier, we can still kind of represent the augmented matrix just by taking whatever was on the left here, slapping it there, putting a line down the middle, and then taking whatever was B, putting on the right. Why this matters is that then when you do an operation on the left, you know you're doing the corresponding operation on the right. All right, and these are going to be called elementary row operations, which we're going to chat about in a second. So in this form, it becomes easy to use elementary transformations to change the matrix into row echelon form, followed by reduced row echelon form. So two concepts, but ultimately, the whole point of using these operations is to change my perspective of the problem into a way where it's easy for me to read off the solution. As you just saw by the previous example, it was easy to solve that because I had a 1 and a 0 under each of those columns, right? That meant that I was speaking in terms of my elementary units, okay? In that case, it was nice. It was wood and steel. But it's not always going to be that. Maybe I had 4 different products, okay? Both using wood and steel. I still want to use the same resources, but for whatever reason, I don't sell those individual items. I actually produce 4 different ones of them. Well, the same story is going to hold, right? We're still going to do the same thing. There's still going to be ways to get a particular solution and then change how many of each product I produce, right? By finding those ratios between them. And that's still going to always be the same story. And that is ultimately what row echelon and eventually reduced row echelon form get you. It gets you those ones and zeros, and it tells you that perspective. A lot of the times, what we engineer there, how we engineer those ones and zeros matter, okay? Singular value decomposition, for someone who was asking me about principal component analysis earlier, that is a meaningful change of perspective, because what we're doing is we're going from talking about our features to talking about combinations of features that have high variance. So I can't always tell you what the columns mean, but being able to understand and extract those columns from the problem is what makes the data science. It's what makes this useful, right? More often than not, and again, there are particular representations of these matrices that work and engineer these zeros and ones properly. They will then tell you a lot about your problem, your eigenvectors, your singular vectors, right? Cool. But for now, all we have to care about is how to solve these linear equations using elementary transformations. I'm not going to show you it this week. I'll maybe do it at the start of next week. But every single one of these elementary transformations corresponds to a matrix multiplication. So if you like to think only in terms of manipulating matrices with matrices, which I think is a very safe perspective of linear algebra, by all means, consistent here. Okay? You can think of all of these things just in terms of the matrix multiplications. But what's also nice is sometimes, it's just easy to remember that you get your matrix into augmented matrix form, and then you do these three operations, and they just kind of, you've memorized them almost. And again, a lot of mathematics is knowing when to use what trick. And in that case, if you want to memorize these three operations as their primitives and abstract away all of the geometry, fantastic. That'll get you through, right? And then when we talk about geometry later on, you'll forget the elementary row operations, and you'll remember that what we're doing is inverting a matrix on the left, right? Because the whole point of this, in fact, we'll come to it in a second, and I'll draw it out there. But the whole point of this is that you're inverting the problem. You're getting those ones and zeros like an identity matrix. And so you don't always have to be holding all of mathematics in your mind and being completely consistent all the time. Sometimes you might just want to say, what are the three row operations I can do? Trust the fact that they were derived properly. Trust the fact that you can derive them properly. But it's maybe not always necessary to kind of always be doing things from first principles. Okay. So the elementary row transformations that we can do is exchange two equations. So the rows in the matrix representing the system of equations. We don't really care whether or not there is no meaningful ordering to the resources that we use themselves. Like steel and wood, I can put it on top or on the bottom, who cares? So I can always exchange those rows as long as I'm consistent about it, right? I don't want to now start saying that, one representation is steel wood and the other is wood steel. Now you're going to have a problem. But as long as you are always being consistent about the rows, what they mean, you're fine. And you can exchange them, interchange them. Okay? You can always do a multiplication of an equation with a non-zero real valued scalar, right? So you can always think in terms of bigger quantities. So maybe I am not a desk manufacturer, I'm a pack of 10 desk manufacturer. Same story. Now you're just selling packs, and you're still going to end up, your answer will come out to probably a fraction. So instead of selling 10 desks, you will sell one pack of 10 desks. But your answer is the same, it's just represented differently. And that's what the multiplication by a scalar on the row is doing, right? But it helps you to change your perspective of the problem sometimes, okay? It helps you to say, I'm selling packs, let's say, in some problems. Okay, and then lastly, you have the addition of two equations, and you can just add these two rows together, and in which case now you are dealing with combinations of resource use, right? So I can now change my perspective of the problem. So instead of just saying, I want to produce one desk, now you're going to say, well, I'm actually going to produce one desk and a chair together, right? You can combine them, but your resource use stays the same. Okay, and ultimately that real kind of combination is where things become interesting, because now what you're saying, let's use the earlier example when we had those ones and zeros, right? That was a one at the top corresponding to, this one at the top corresponding to wood over there, right? If I added this row into there, I would end up with this. Now I've got 1, 1. I'm talking about an entirely different product now. I'm talking about an entirely different thing. Now I've got some element of this which is now talking towards a wood and steel package or something like that. But it's still the same problem, right? You can always package these things differently. And that's the kind of whole perspective that we're taking, is how do I change how I package my resources or my products into a way that will be useful. All right. That's the 3 elementary row operations. They do not change anything. The reason you can't swap around your columns is because you already kind of have to be consistent then with the matrix multiplication, right? Because the matrix multiplication says if column 1 times by x1, column 2 times by x2, all right? Again, if you do it from like first principles at the top, you can move things around. But ideally, the only things you can do once you've defined your system of linear equations, once you've set up the problem, is swap rows. Okay. And now we get into our first big definition, which is row echelon form. So a matrix is in row echelon form if all rows that contain only zeros are at the bottom of the matrix. All right, so we want to have like that. If that exists, it cannot be anywhere else in the matrix. All right, it has to be at the bottom, and you can obviously stack them if you have 2 rows like that. And then looking at non-zero rows only, then the first non-zero number from the left, which is also called the pivot or the leading coefficient, is always strictly to the right of the pivot of the row above it. Okay, jargony way of saying I want to have the staircase kind of representation. All right, so I don't want to have a 0 here and a 4 over there. Okay, that's going to cause me problems. So instead, what I want to do is I want to say all, if that's my pivot, then this must all be zeros, and then this pivot must be to the right of the previous pivots. Okay, so this is actually the pivot. Pivot. Okay. And what this is doing for me is giving me this perspective that I was talking about. While you slowly manipulate out this matrix, you're not changing the answers. You're not changing your choice of x's. What you're doing is you're changing your perspective of the problem to being a case now where I can actually just pick my, get ones in the right places where I can read off the solution. The whole point of this that I want to get through is you've got to stop thinking about linear algebra in terms of like, I have solved something or I've changed something about the problem. You haven't. The problem exists. What you're doing is you're changing your perspective of it, which ultimately is, you call it a basis. We'll come to it, but it's a basis. You're changing your perspective of the problem in a way that helps you just read off the solution that was already there. If you're smart enough, you could guess your x's in this case, right? You could guess your x's here. You could, I don't know, yeah, maybe you're an oracle and you could know it. All right, but most people aren't. Big problems get hard, and so we want to learn ways to re-represent problems in ways that we become easy for us to do that. Okay. And so we come to solving systems of linear equations. But before I move on, does anyone have any questions? Are we good for now? Cool. I don't think anyone's online, but
how do you share the link? Do you share it every day or every after?
it's on the course outline. Yeah. Cool. All right. So the way we solve systems of linear equations. Right. So first thing you do is you're going to transform into an augmented matrix. Right. So you just take A and append B, the B column on the right hand side. Right. We're going to turn that into reduced row echelon form. Right. Your augmented matrix is now going to go into reduced row echelon form. And if A was invertible, and I need to fix that too. Why is this not working? Oh well. So if it was invertible, then we apply the elementary transforms to B. As we did the transformation, the resulting right-hand side of the augmented matrix is in fact our solution. So if it was invertible, what we're going to get is on the left-hand side of this matrix is going to become 1, 0, 0, 1. In the exact same way as our previous problem, we've now just able to read off a solution, right? And again, what we've done is we've inverted that problem so that we now represent it in a way that's easy to do that. All right, if it was not invertible, then we either arrive at a contradiction, and I've drawn an example of a contradiction just above it there. So you have that last row is 0, 0, 1. So what that's essentially saying is that I have some kind of linear, or I have some combination that will use no resources, all right? None of my products use steel, but somehow I want to now, make sure that my 1 unit of steel on the floor is being let gone. Obviously, that doesn't make sense, okay? And the whole point is that when you represent, these problems in this way and you get to a contradiction, it should be really easy to understand why if you gave meaning to the system of linear equations, right? If you know what your columns mean. Okay? And so in that case now, a good question is to ask, well, how close can I get? What's the best kind of alternative I can do? And we'll kind of come to that. And another option is you can always ask, is there multiple solutions? Can I move around in this null space? We'll consider examples of both. And it's worth mentioning that generally the transformation is done using an algorithmic approach called Gaussian elimination on a computer, or rather a numerically stable version of it. But we're not going to get too into like the computational side of that. It's just an efficient algorithm. But essentially what you do when solving these things using these elementary row operations is a version of it. It's a slightly more flexible version of it because computers obviously need rules. You guys can use your intuition. All right. Let's see, how much more do we have? Do you guys want to take maybe a quick 10-minute break and we'll come back at 4 and we'll just do these final examples? Sweet. Alrighty, should we get started again? Alrighty, so we have an example set up here now of a matrix that's been put into an augmented matrix. We're not going to play the game now of trying to like map concepts onto it. What we kind of want to do is switch between what we're trying to think and hold in memory while we're doing mathematics. So we've had this example now of desks and chairs and metal and all that, and it's become quite tired. Let's just figure out how to solve it, and trust that whatever we're doing with these columns is now practically going to work out for us. But we've learned how to represent the problem, right? We've learned how to think about columns as being entities within the world, rows being our budgets, or kind of mapping from those entities to some sort of budget. And then on the right-hand side, we have our total, okay? We know how to form problems. Let's just solve it. Okay, and so we have our three elementary row operations. Each of them corresponds to a matrix. But we know that, for example, we can swap row 1 and row 2. And what we're always trying to do is just get zeros there, right? That's the first thing. We just want to get zeros under our column. However we do that doesn't really matter. So that Gaussian elimination algorithm that we had, it doesn't really do too many row switches or anything like that. It just starts doing divisions, okay? And it just runs down your columns and manually puts ones and zeros in that place. We're slightly smarter, okay? There are cases when we might sit there and think to ourselves that we can do it slightly better. So, for example, if I gave you this problem, which was a 1, 2, 3, right? We want it in reduced row or row echelon form. We would just swap the two rows, and we get 1, 2, 3, 0, AB. Okay, all right. If we're starting to do divisions, we would then kind of have to move things around. The one issue is also that division algorithm, and that's why it was a numerically stable version of Gaussian elimination. You obviously can't start doing divisions with like 0 and stuff. So you've got to be a little bit careful if there's zeros in the matrix. In this case, it is kind of easiest if we maybe just swap row 1 and row 2, because we can see that there's already a 1 there in that second row in the right place, and so we're just going to do that. Okay, and practically speaking, when you do your tests, and maybe these slides are the practical get through MFDS slides of this today's lecture, please try only do one operation at a time for your own benefit, but also just like your marker's benefit and things like that. Obviously, we do our best for you. We're looking for your marks. But if people will start doing like 2 times R1, swap R1 with R2, like, things get messy quick. And so I recommend when you're doing row echelon form, you do when you're getting it into row echelon form, you do one operation on a row at a time. Okay? Take as many pages as you need, represent however you want, but try just do things in systematic steps. So for example, here we're first going to swap row 1 and row 2. After that, we're now going to say, I'm going to subtract 2 of row 1 from row 2. Okay? What that'll do is that'll give me a 0 there. I'm also going to now try and add back 3 of row 1 into row 3. That'll get me my 0 there. As you can see, these decisions we made here were only focused on getting zeros there. We didn't even consider anything else about what was going on in this problem. All I did was say, I put my 1 in the top left column, check. Top left index, check. Now, let's get zeros everywhere else. Okay, and that's the method. That's the whole iterative approach you're going to do. Get a 1 in the index you wanted. Use it to put zeros everywhere else. Get a 1 in the index you wanted. Use it to get zeros everywhere else. All right? And that's the whole long spiel of this. If you follow that method, it'll work. So now in this case, we have zeros over here. So we know that whatever operations we're going to do, as long as we don't start swapping rows back, we're always going to have a 1 here, right? There is never going to be a case where I'm going to add a multiple of that row back to row 1, where it's going to change that value of 1, because it's always going to be a multiple of this 0 there. Okay, so what this means is now that we have zeros under the 1, we're safe to just keep manipulating the next two columns. And we can do that systematically. Okay, so we were lucky here, we already had a 0 up top there. In row echelon form, we don't have to worry about it. In reduced row echelon form, we will try to put a 0 there. But in general, we just now, our next goal is just to put a 1 over there. Okay, so that's all that's going to happen. Is now we're going to take first step 1. As you can see, they're now doing 2 steps at once, which again I recommend against doing. But firstly, what we're going to do is just multiply row 2 by 8 over 5, and then we're going to swap it around so that now we get our 1 over there and our 0 underneath over there. Okay, you guys can verify the actual mathematics of that. But all that's doing is just trying to engineer the 1 there and the 0 underneath it. They did 2 steps in 1. And now lastly, we now just need to get our 1 in the third column there. All right. And so we're just going to multiply that row by negative 5 over 142, which is just the reason there. It was negative 142 over 5. And as a result, we now have 1s on our diagonals. And so we are in row echelon form. All right. The first non-zero number to the right of the pivot of the previous row is 1. Okay. So the pivot of the top row is going to be a top left index. And then we know that underneath it, we need a 1 followed by the next row's pivot. Underneath it, there's a 0, there's a 0 followed by the next row's pivot. And so we have that staircase kind of pattern. Okay. And then lastly, if you really want to keep going, you can get into reduced row echelon form, which is now when you also start engineering kind of zeros towards the top here. Makes life a little bit easier, and that's what they're doing now. So what they're going to do is they're going to take 5 of row 3 and add it back to row 1. Again, because we have these zeros here, there's no risk of us actually breaking anything we did before. And then lastly, here we're going to also then on the second row, we're going to add back negative 9 over 5 of row 3, so that becomes a 0 as well. And so what have we done? We've now re-represented our problem in a way that we're speaking in terms of entities that have 1s and 0s kind of in this matrix, all right? We are now speaking in terms of individual entities that are decoupled. Decoupled because they have no entries on the off diagonal. And so we have now put our problem in a really nice way that we can just read off our solution. There we go. That is then the particular solution of this case. Okay? And then lastly, since in this case there are 3 equations, 3 unknowns, we have 3 solutions, there's no general solution, there's just one. You know that this is going to be your final case. If you have columns that are sticking around over here, then you're going to have infinitely many solutions. And then if you get to a case where you now have 0, 0, 0, 4, or something like that, you've got a contradiction. Those are the only 3 outcomes of this. Okay? You're either going to get to a case where you have a contradiction at the bottom, and then there's no solution, or you're going to get to a case where you get this perfect structure around here with your 1s along the diagonals, and it's in row echelon form, and you can read off a solution. Or you're going to get to a case where you have 1s along the diagonals and some additional structure on the right-hand side, in which case you can have infinitely many solutions. All right? Yeah.
Sorry for going big.
No?
So when we are reducing on the first step, can you go to the previous step?
Yes.
I don't know if I'm overthinking. When we are now after swiping row 1 and row 2, when we are producing the second matrix, when we say negative 2 times row 1, are we not supposed to say negative 2 row 1 plus row 2? So that we
You want it written like R2 is equal to R2 minus 2R1?
yes.
Yeah. That's essentially what this means. This isn't a set notation of how to write this. This is just telling you what the row echelon forms was, what operations were being done. I would recommend that you do try and, if I do it, and in the memos that I show you, I tend to do it this way. All right. But that is the operation that's happening. Any other questions? We good? Yeah.
You spoke about a case where you have something on the side of your ones on the diagonal. Could you give an example
Yeah, I mean this earlier one, right? Let's see if I can find it quickly. I mean this would be another one, right? Yeah.
So that matrix would have infinitely many solutions.
Yes. Yeah. Whenever you have more columns than you have rows, unless one of these columns ends up being like 0 there as well. Like if a column zeroes out, then it means that it wasn't adding any information to it. There's no kind of relationship between like wood and steel or so on, and desks. You good? Cool. All right. Let's now consider this problem. So you're gonna do you guys can check it at home. But in this case, what we ended up with was a solution at the bottom with all zeros. All right. I recommend for some practice you go through this. I know it's pretty tedious to do it for most of you, I think. And so now what we have is the left-hand side is not an identity. So we have not encountered a contradiction because we essentially just have all zeros there, right? So there's no contradiction. It would have been a contradiction if this was any a value where a is an element of the reals. Now it's a contradiction. But because it's 0, what we're saying is that I have no steel in my factory and I don't produce any items that use steel. And so this is just not a feature that I even have to care about. Not a contradiction, just not, it kind of removed itself from the equations. And again, that's the whole point of doing this. We're re-representing problems in a way that show those true facts about the problem. Okay, and so now we want to obtain the particular general solution, and this can be done as before, but the reduced row echelon form makes this easier. Okay, so to obtain a particular solution, we express the right-hand side of the equation using the pivot columns on the left-hand side, right? And again, what we're doing is that this is essentially saying we're doing that matrix multiplication that I showed you earlier, when it was A1 column x1 plus A2 column x2. That's what that statement is saying. Okay. This can be done in row echelon form, but it's much easier in reduced row echelon form when we get back to this kind of a diagonal matrix with no zeros above the ones either. Okay, so in this form, once it's in this reduced row echelon form, it's now easy to just read off the solution. They switch to lambdas instead of x's, but ultimately I'm just going to set my first variable to being -2. Okay, and secondly, my second variable is just 1/4. And I'm just matching up those variables. And so if we write it back in the system of equations way that we were doing earlier, what this corresponds to is 0, 0, 1, 0, 1, 0, 7/4, 0, times by x or lambda, whatever you want. X is equal to -2, 1/4, 0. And so what I'm reading off here is just what values I'm going to be setting for x1, x2, and x3 such that this holds. Okay? x1, x2, and x3. Excuse the handwriting. Yep.
So this matrix should be considered the row echelon form.
This is reduced row echelon form.
Reduced, even though there's no zeros at the third column.
That's a good question. Oh, no, so to do reduced row echelon form, you only need zeros above these pivots.
Oh, so only zeros above the pivots.
Yeah, exactly.
Okay, thank you.
Everything else is arbitrary. This is kind of to make your case. This is another example where you now have that structure to your right-hand side. Okay? So all we're doing now is saying, can I read off my solutions from x1, x2, and x3? And we know that with matrix multiplication, what's going to happen is I'm going to go 1 times x1, 0 times x2, minus 5 times x3. And it must give me something helpful to represent the right-hand side. So I'm just going to use x1 to make sure that I only deal with -2. Okay? So what value of x1, when multiplied by that, gives me -2? It's just -2, right? Like it's not play that game. Same thing for x2. What value of x2, when multiplied by that column, just satisfies 1/4? Okay? It's just 1/4. And so that's why we're now reading off these solutions. Okay, we've put it in a form where that's really easy to say what x1 and x2 should be. All right. So now what we want to do is we want to obtain the general solutions. That gave us a particular solution. We know that we've satisfied these conditions because after that, I'm just going to say x3 must be 0. Okay, I used x1 and 2 to satisfy my conditions. I don't need to think about x3. I'm going to set it to 0. And that's what we're doing over there, right? So now we're going to look at the -1 trick. So remember earlier when I was showing you those matrices, what we were doing is we got something like, 8, 12 is equal to 8 times 1, 0 plus 12 times 0, 1. And then we always said that we could take it over and we get that negative number, right? We could always represent it in terms of the null space and say 0 is equal to, I'm going to write it up painfully, plus 12, 0, 1. And then we would then have minus 8, 12. That fact is what the -1 trick is doing. We're just going to always say, okay, well, there's a -1 there always. We see that when we write it out this way. So now we're just going to make that a standard thing when we solve these general equations. And that's all the -1 tricks do. Okay? This. All right. So let's assume that A is in reduced row echelon form or in row echelon form. Okay, it is a K by N matrix, and K is less than N, right? So it has less rows than it has columns. So you know you're going to potentially get multiple solutions. All right, so assume there are no rows with only 0 elements. So we have now dropped that row. If you get to a case where this is your solution, the first thing you want to do to get your general solution is just delete that row. Just remove it. You're literally going to write out 1, 0, 0, 1, -5, -7/4, and so on. Okay? First part of the -1 trick is doing that. If you don't, you'll get one too few dimensions to your null space, which will be a problem. So remember to delete it. Then what we're going to do is we're going to now add new rows to that matrix until it is an n by n matrix, until it's square, until it has the same number of rows as there are columns, right? We're going to call that A hat. Okay? If I had n columns and k rows, then I want to add the difference between them until I get to an n by n, right? So I'm going to add n minus k rows to it, so that ultimately what I have is n minus k plus my original k rows, which is then just n rows, right? All checks out. And in this case, what I'm going to do now is that I want to make the diagonal of these new rows that I add -1. Okay? In this case, all my pivots will now be 1 if I'm doing this in reduced row echelon form, which again is probably what you want to do. All my columns are now going to be 1 or -1, which means that I can very easily read off a solution. Okay? Then the columns of A hats that contain the -1s at pivots are solutions to this system of equation. Okay? AX equals 0. We know that for a fact, right? Because again, we had that original representation of 8 and 2 is equal to 8 times 1, 0 plus 2 times 0, 1, and so on. And we just take it over to the other side. This act of taking it over to the other side is what gives us that null space now with X. Okay, so this was our original problem that we saw, right? We just read off that our particular solution was -2, 1/4, and then 0 for the third dimension. We're going to delete that row, okay? And we're now going to append the same number of rows we need to get back to being a square matrix, all right? So we have 3 rows, 3 columns, all right? And in the diagonal element of our new row, we're going to put a -1, okay? If you were in a case where, let's say you had 1, 0 -5a, 0, 1 -7/4b, then we were going to add 2 new rows, right? And you're going to go 0, 0, -1, 0, 0, 0, 0, -1. Okay, you see how this is always along the diagonal. All right. You can then just read off this column here as your general solution. That will always just give that. As many columns as you have minus ones off the end of it are your general solutions, and you always remember that you can multiply it by lambda 1. Lambda 1 is an element of the reals. Okay, and so you can add back any linear combination of this vector to your original solution, and it's going to be just moving around the null space. It's always going to give you 0. Okay, and the way you can check this is by actually just doing this multiplication, right? A times that x must give me 0. Okay, so if you went and did 1, 0, 0, 1, minus 5, minus 7 over 4, and you multiplied it by this vector here, minus 5, minus 7 over 4, minus 1, running out of space. Okay, matrix multiplication, you take your first index, that's 1 times minus 5. The 0 cancels out there. Let me switch colors. This 0 cancels out that number there, so you don't care about it. So ultimately what we get is 1 times minus 5 plus minus 5 times minus 1, 0. Okay, same story for the next one. So there's there. You get 0 times 1 minus 5, gives me just 0. And you have 1 times minus 7 over 4 plus minus 7 times 4 over 4 times minus 1 gives me 0. I recommend you always do this check in your exams when you solve this, right? You take that part of it, you multiply it by the original matrix, you can delete the excess row, and make sure you come out to your zeros. If you want to check this even further, what you're going to do is you're going to take this, multiply it by your original matrix, and what you want to get is that AX is equal to B bit of the matrix. Maybe I'd leave that in there for now. We're all happy? Is it making sense? Not seeing too many happy faces right now. Is it just Friday afternoon? I suppose this is a fact of life for us going forward. We are
14 Friday after.
It is a tragedy, I agree. Unless you guys all love maths. I mean. All right, let's wrap up so you can all go to your plans. In order to find the inverse of a matrix, okay, we can use the same strategy to find the inverse of a matrix, right? So what did I define an inverse matrix as, right? I said that an inverse of a matrix A is any matrix B which gives me an identity matrix. That's just a new system of linear equations, yeah? What this is then saying is I'm going to, let's see, let's redo this. I am going to take A, put I over there, and I'm going to run through the exact same process I just ran, and my solution to that will now be that matrix B that inverts it, all right? Because ultimately I'm going to be going, the fact that I can then get this into reduced row echelon form means that it's going to go 1, 0, 0, let's just go 2D, 0, 1, times by some matrix. I know that that's going to be the inverse of A, by fact that it was what gave me an identity matrix on the left. Okay, what this is the same as saying is just going A inverse there, A inverse there. Okay, and what I'm left with is now on the right hand side, that cancels. B is equal to what is ever on the right hand side. Okay, so it's just a perspective of inversion that says that inverting a matrix is just another system of linear equations that I now know how to solve. All right, so let A be an n by n matrix. Again, if it's not n by n, we know it's not going to invert. Right? It has to be a square matrix to be invertible. The inverse is the matrix X that satisfies this equation by definition, not something to even think about. We defined it as that. This is fundamentally a set of systems of linear equations, and we can use the augmented matrix notation for a compact representation from this set of systems of linear equations. Okay, and again, that will give us your answer. One important thing to remember is if some people like to do, different versions of this, and I'm totally fine for you guys to approach tests however you want, do whatever method you want in tests. We'll do our best to mark your approach. But just remember that this is what you're doing when you're solving systems of linear equations. You're going A, x equal to B. You're multiplying on the left-hand side. Don't try and get the inverse by doing anything else over here or anything like that. You have to just be really careful that you're keeping these matrix multiplications the same. Sometimes it can work because inversion is commutative. Like we saw earlier that A, B equal to the identity is equal to B, A. All right. We know that that's true. That's an identity. But sometimes if you're not super careful with the way you approach the systems of linear equations, what you're ultimately doing is multiplying on the right-hand side instead of on the left. And I'll show you an example of that at a later kind of point. I think it's not super helpful right now, but just keep kind of your wits about you when you're doing these abstractions of matrix multiplication, like reduced row echelon form, elementary row operations. Okay. So what do we do when our system does not have an exact solution, all right? Can we still, under some mild assumptions, such as all columns are linearly independent, find an x close to solving the system, all right? And so the answer is yes. There is a way to get this up to rank. And so what we're going to do is we're going to multiply. You're going to take your system. You're going to multiply on the left-hand side by A transposed, right? You do it on both sides. Because those columns are linearly independent, what we know is that we will now get a full rank A transpose A matrix. Okay, that's the assumption of the problem. Linearly independent rows means that is how many matrices you have that you cannot be written as a form of each other. All right, and we'll come to that again in future weeks. We revisit Mo-Penrose's inverse. So if it's not super clear on that point now, don't worry about it. But the point is that you know, because they're linearly independent columns, that when you do A transpose times A, it will now be full rank. Full rank means that you will not get a contradiction. You know that it will have as many rows as it will have columns, and you will never ever engineer a situation where you're going to get like, A, B, 0, 0. This will never happen because of the linearly independent column assumption. The good news of that then is I know that's full rank, which means that it's invertible. And so I can now just invert both on either side. I'm going to go O transpose times A. I know, in fact, I've written at the bottom here. Okay. I'm going to take my original form of that, which is up there. I will now just multiply by A inverse A transpose A inverse, my bad. That will cancel. This entire thing now becomes the identity matrix. And what you're left with on the left-hand side is just the identity times by x. And so you have x over there. Whatever you do on the left-hand side, you need to do on the right. So initially, again, we multiplied by A transposed, actually. Transposed. And then after that, we did the inverse of A transposed A. All right? And so now we get to what is called the pseudo-inverse. And that is a solution to our problem. What it actually corresponds to is the best approximation to our problem. Okay? When you're doing linear regression, this is actually what you're solving. All right? You're finding the best kind of line that fits into your subspace. That is also the same as solving the best approximation of these linear combinations. Okay? Again, those perspectives will start coming together when we get to regression. Okay. And I think we will end it there for today. Next week, we will pick up with groups. If you want to read a little bit about them so that this notation doesn't look so silly next week, then that's fine. Otherwise, they're not exceptionally difficult. Before you all pack up, does anyone have any questions? Cool. All right. I'll see you guys next week.
Contradiction. The contradiction, the devil.
Yep.
If I was going to put a 1